Okay, let's talk about infrared spectroscopy. If you look at the electromagnetic radiation spectrum, infrared is just here at longer wavelengths than visible light, and UV is at the other end, just past the blue light end of the spectrum, or violet. Now, infrared that we're interested in is around this region of wavelengths around the micrometers to tens or hundreds of micrometers. A reminder that wavelength is the distance between two consecutive points on a wave, so the peaks or the troughs. Now, it's important to understand when we're talking about infrared spectroscopy how the energy levels within a molecule relate to how that molecule can absorb or emit radiation. So if we have an energy level within a molecule of some type, it could be a state of some type, and then we have another state of that molecule, another quantized energy level. If we put energy in the form of electromagnetic radiation into that system, we can promote the system up to a higher energy level. But the energy there has to be the same as the gap between those energy levels. So the energy of the radiation must be equal to the energy difference between those two energy states. Now, it turns out that infrared radiation is around the same energy as the difference between energy levels within molecules that corresponds to them vibrating. The atoms within molecules vibrating, either stretching or bending like this. So the molecules are distorting in some way. And that energy difference between different energy levels corresponds to the infrared spectrum. Now, how does that benefit us? Well, the energy at which the molecule absorbs the radiation, according to these vibrations, tells us something about the functional groups within that molecule, which is a really useful thing to us. So here's an example of a infrared spectrum of a molecule. So this is acetyl salicylic acid, or aspirin. And you can see it's quite a complex spectrum. There's a lot of peaks here, and there's some gaps where there's not much happening, and then a very big major peak down here. Now, for historical reasons, there's two unusual things about infrared spectra. One is that we use a unit of measurement called the wave number, which is centimeters to the -1, or reciprocal centimeters. So there's a bit of a strange unit, and because it's the reciprocal of a distance, it actually corresponds to a frequency. So high numbers are high frequency and low numbers are low frequency. And frequency correlates to energy. So these are high energy transitions and these are low energy transitions down here to the right. So the part of the infrared spectrum we're interested in is from 4,000 reciprocal centimeters to about 400 or 450 reciprocal centimeters. And even though the spectrum is very complex, it has two major things that it gives us. One is there's certain regions of the spectrum that tell us what are the functional groups within this molecule, or what are the types of functional groups. And a large part of the molecule, particularly down here to the right-hand side, is distinctive for any particular molecule. So we call that a fingerprint. So if we take the spectrum of aspirin, and then we take the spectrum of another sample of aspirin, we would expect this fingerprint region to be very, very similar between those two samples. In fact, it should be identical, but obviously with an experimental error. So what do we mean by molecular vibrations? Well, the atoms in the molecules are joined covalently to each other, and they can vibrate. So the bonds can stretch like this, or there can be bonds that bend so the atoms move relative to each other. So the simplest vibrational motions are those stretches, two atoms going closer and further away from each other, and the bending motions where the angle between those two atoms is changing. So stretching vibrations look like this. So because molecules are quantum systems, we're not just talking about simple one bond stretching at a time. We're actually talking about how the molecule, subunits of the molecule, can bend or stretch in ways that are related to each other. So a CH2 group might have a stretching frequency that is related to both the CHs, both the hydrogens attached to a carbon going synchronously with each other. And then we might have an asynchronous one where one comes closer while the other one goes further out. So they're what we call different modes, different vibrational modes. So this is a symmetrical stretching here, where there's both bonds are lengthening at the same time or contracting, and an asymmetric stretching where they're in opposite directions. The bending vibrational modes are more complex. So there's things like scissoring, there's rocking, there's wagging, there's twisting, all sorts of different possibilities. And because there's many different ways that can occur, they can be difficult to predict and in many ways not as diagnostically useful to us. So through a lot of experiment, organic chemists have managed to develop correlation tables that tell us what kind of vibrations correspond to what frequency within an infrared spectrum. So most functional groups we're interested in have stretching vibrations in the region 3650 to 1500 reciprocal centimeters. The area between 1500 and 400 reciprocal centimeters is what we call the fingerprint region. And in this region, we've got a lot of complex modes that are difficult to predict, and there's a lot of overlap between different modes of different functional groups. So that is diagnostic for a particular molecule, but not particularly consistent for classes of functional groups. So we'll tend to focus more on these higher frequency stretching vibrations. So let's look at some. So we've got OH groups tend to have stretching vibrations between 3200 and 3500 reciprocal centimeters. NH groups fairly close by, 31 to 3500. There's also differences in how strong, how intense the band is. So OH bands tend to be strong and quite broad. NH tend to be a little bit less intense. CH stretches tend to be medium to strong, and they're between 2850 and 3100. Carbon-carbon triple bonds, 21 to 2260, but they're quite weak. CO double bonds, very strong stretches, 1630 to 1800. CC double bonds, only weak and in a similar region, maybe more towards the 1600 side. And CO single bond stretches, very strong, and they're actually down in that fingerprint region, 1050 to 1250. So maybe there we may be able to see them, but they can be sometimes a bit buried or clustered around other peaks. Now, there's a few rules of thumb here about vibrational infrared spectroscopy. We don't have enough time in this video to go through all of the reasons behind this, but we'll just note a few general trends. So one really important general trend is the stronger the bond, the higher the frequency of the vibration. So imagine the two atoms are held together via a spring. A single bond will have a relatively weak spring compared to a double bond, will vibrate faster, and then triple bond has a really strong spring, so it will vibrate really, really fast. So a CC triple bond has a stretching vibration 21 to 2260, whereas the double bond is 1600 to 1680, and single bond is all the way down at 800 to 1200. So a very big difference in the frequency there. The stretching frequency also is related to the mass of each of the elements. So it decreases as the mass increases. So we know that carbon, whereas we're dealing with organic molecules, we're mostly interested in carbon bonded to something else. And so carbon bonded to hydrogen, hydrogen is very light, and so we have a high stretching frequency. Oxygen is more massive or has a higher weight, and so the frequency goes down. Chlorine is higher in mass again, so the frequency is even lower still. Now, an interesting side effect of this is that we can have isotopes that differ in mass compared to other isotopes. So one of the most common isotopes we use in organic chemistry is deuterium. So deuterium is simply the 2H isotope of hydrogen, and that has a different, when it's bonded to carbon, it has a different stretching frequency than the 1H isotope. And so we can actually see differences between isotopes in infrared. So we said before, bending is the other major type of vibrational bending is the other type of vibrational modes that we can have. They're usually at lower frequency than the stretching modes. And lastly, the hybridization of the atoms that are part of this vibration has an effect on the stretching frequency. So as we go from sp3 hybridized to sp2 hybridized, we go to higher frequency, and then sp hybridized is higher frequency again. So this is not talking about the triple bond. We're talking about the carbon-hydrogen bond, where we're talking about the carbon as being sp hybridized because it's part of a triple bond, but we're talking about how that affects the hydrogen that it's attached and the strength of that CH bond. It's actually stronger and vibrates at a higher frequency. Okay, so looking in a bit more detail at hydrocarbons, if we have alkanes, we have stretching around 2850 to 3000. That's the stretching mode. The CH2 groups have a bending modes around 1450, that's only medium strength. And CH3 groups, they're a particular facet of hydrocarbons. They have a bending mode around 1375 to 1450, which is only weak to medium. Alkenes, the CHs will be at the higher frequency end, 3000 to 3100, weak to medium, whereas the CC double bond will be 1600 to 1680. Alkynes, the CH will be higher frequency again, and the CC triple bond would be in this really diagnostic 21 to 2260 region. So this is a lot of numbers, but let's have a look at some examples to try and put it into place. So here we've got 3 examples of hydrocarbons. The first one is just that a straight chain saturated alkane. And so it's a very boring spectrum, really. We have CH stretch here. So there's a few different peaks, a few different CH stretching modes. There's a CH2 bending mode here. And then there's a CH3 bending here. And there's not much else around the fingerprint region for this simple unbranched alkane. Okay, what if we have a cyclic alkene? Now we get a significantly more complex spectrum. We've got a higher frequency CH stretch for the hydrogen that's attached to the sp2 hybridized carbons. So you can see that is missing in the alkane here. So that's at about 3100 or so. We've got the CH stretches for the sp3 hybridized carbons, and then we've got the CC double bond stretch around 1600. So it's only fairly moderately intense, and then we've got a variety of peaks in this fingerprint region down here. And then finally we've got an example of an alkyne. So this is a terminal alkyne that has a CH group. So here we can see the CH group all the way down here at about 33, about 3,300. And that's completely missing from the other 2 spectra. So you can see it's much higher frequency because of that stronger bond between a hydrogen and an sp hybridized carbon atom. We've got our CH stretches of the sp3 hybridized bonds. And then we've got this peak standing out like a sore thumb here of a carbon-carbon triple bond coming in at about 2100 or so. And that's completely missing from the alkene and missing from the alkane. And then we've got some CH2 bending and some CH3 bending in this region, and some peaks down here in the fingerprint region. So we can see how infrared spectra can tell us whether we've got an alkene, an alkane, or an alkyne. Let's have a look at some oxygen-containing molecules. So here we've got an alcohol. It's just a straight chain alkanol. And we've got a really large, broad, intense peak here for the OH stretch. And it peaks at around 3,300 reciprocal centimeters or so. So that's really characteristic of an OH stretch. And it's so strong that it continues here underneath the CH stretching here. So that's why I've sort of outlined it like that. We've still got our CH stretching for all these sp3 hybridized carbons and their associated hydrogens, CH2 bending, and then we've got this fairly strong CO stretch from the carbon-oxygen bond here. And a few other peaks around the fingerprint region. Now, if we compare that to this molecule, this is a very similar structure. It has just carbon, hydrogen, oxygen. However, it's an ether, so it has no OH bond. And so we're completely missing that OH stretch that's present in the alcohol. We've still got the CH stretching here, and we've got our CH2 bending, and we've got CO stretching, very strong CO stretch here, which is a little bit shifted, but fairly similar to in the alcohol. So it's around 1,100 and around 1,050 in the other compound. Here we've got a couple of molecules with other functional groups. So the first one is an aromatic molecule. So we've got our CH stretches, and these CHs, apart from the CH3 group here, all the other CHs are bound to sp2 hybridized carbons. So they're a bit further at higher frequency here. And then we've got these little peaks here. We won't go into what they are from, but they're more complex vibrational modes of the benzene ring. So it's really indicative of benzene rings to have these little tiny peaks here in the region between about 1,700 to 2,000. And then we have the benzene ring has these, it's a delocalized structure. So even though we draw with double bonds, we've got a delocalized structure with some overlap of the pi system around that ring. And so each one of those carbon-carbon bonds is somewhere between a single and a double bond. And they have vibrational stretching modes in this 1,500 and 1,600 region, quite sharp like that and quite strong. And then we've got some CH aromatic bending here, so quite low frequencies. They're CH bonds that are bending out of the plane of the ring. Let's compare that to an amine. So this is a simple unbranched alkyl amine. And here we've got two peaks for the NHs of this molecule. And you might be tempted to say, well, there's two hydrogens, so that's why we have two peaks, but it's not that one peak is from one hydrogen and one is from the other, because in a quantum sense, they're equivalent. What they're from is one is from a symmetrical stretch like this, and one is from an unsymmetrical stretch like this. So they're around 33 to 3,400. We've got our CH stretches, our CH bending, our CH2 bends, and our CH3 bending here, and a few nondescript peaks in the fingerprint region. Okay, and here we've got one of the most useful applications of infrared spectroscopy is when we have carbonyl groups within the molecule. So there's been a lot of experiments to identify how the structure of carbonyl compounds affects the peaks that we see in the infrared spectrum. So this ketone here has a carbonyl group, and that has a stretching frequency around 1,700. Now, one thing I didn't point out earlier is that the strength of the peaks is very closely related to how strong the dipole is of that bond. And a CO double bond is very polarized with a very strong dipole, and we see a very strong peak because of that. So at 1,700, strong peak for this CO double bond stretch. And we've got the usual CH stretching here, and then some other peaks in the fingerprint region. So it turns out in different carbonyl compounds, we see different frequencies and different features of the infrared spectrum, depending on what type of carbonyl compound it is. So a carbonyl group is a CO double bond, but that could be present within a ketone, or it could be present within an amide, or a carboxylic acid, or an ester. Amides tend to be at lower frequency, 1630 to 1680, whereas carboxylic acids tend to be 1700 to 1725, and esters tend to be 1735 to 1750. And we'll see other features. So amides might have NH stretches, carboxylic acids will have OH stretches that are very broad, and esters will have no OH stretches at all. Okay, so final example here is looking at some carbonyl compounds. So here we've got a carboxylic acid and an ester with similar structure. In the carboxylic acid, we've got an OH, so we've got this really broad OH stretch that goes right across here, very intense and extremely broad. The reason for that broadness is that we have hydrogen bonding between OH groups of one molecule to another, and that changes the sort of environment around each one of these molecules. And so we might have OH bonds that at any point in time are of varying strengths depending on how tightly hydrogen bonded they are to another molecule. So we see this really broad peak here. And then it's a little bit of CH stretching peeking out from underneath that. A CO double bond stretch around 1700. If we compare that to the ester, it's just flat in that region where we would expect to see an OH stretch if it was a carboxylic acid. We just see the CH stretches over here around 3000. The CO double bond stretch is there, and it's very similar to what we see for the carboxylic acid. So there's our CO double bond there, and there's some CO stretching frequencies here. Okay, so that's all I'm going to say about infrared spectroscopy. It's really useful to identify functional groups within a molecule, particularly in the stretching region between about 1400 and about 3700 reciprocal centimeters. And we can say a lot about the molecule just from looking for these diagnostic peaks. Okay, thanks for watching.